Hello, stargazers. Welcome back to another journey through the cosmos, where tonight we're going to attempt something that sounds deceptively simple, counting the stars in Andromeda. But here's the thing that kept me awake last night. When a 10th century Persian prince looked up at that faint smudge of light and decided to document it. He had absolutely no idea he was recording something that contained more stars than there are grains of sand on all of Earth's beaches. How do you count something like that? How do you even begin? If you're finding comfort in these cosmic questions, go ahead and hit that like button. And if you want more stories that blend science with wonder as you drift off to sleep, subscribe and turn on notifications. Trust me, we're just getting started. Let's travel back to the year 964 CE to the city of Isfahan in what is now Iran. Picture this: a clear desert night, the kind of darkness we've almost completely lost in our modern world. The air is cool, carrying the scent of jasmine from palace gardens. And there on an observation platform sits a man named Abd al-Rahman al-Sufi, who would become one of the greatest astronomers of the Islamic Golden Age. Al-Sufi wasn't just any stargazer, he was a prince, a scholar, and what we might call today an obsessive documenter. While much of Europe was stumbling through what we call the Dark Ages, losing the astronomical knowledge of the ancient Greeks and Romans, Islamic scholars like al-Sufi were not only preserving that knowledge, they were expanding it, refining it, correcting it. On this particular night in 964, al-Sufi was working on something extraordinary, a complete revision of Ptolemy's star catalog, which had been the astronomical Bible for over 800 years. He was checking every single star Ptolemy had recorded, verifying positions, correcting errors, and adding his own observations. It was meticulous work, the kind that required patience, precision, and phenomenal eyesight. And then he saw it, or rather, he had always seen it. But on this night, he decided it was important enough to record in detail. In the constellation that Arab astronomers called Al-Mar'a al-Musalsala, the chained woman, what we know as Andromeda, there was a small, faint patch of light, not a star exactly, something else. He described it in his masterwork, the Book of Fixed Stars, as a small cloud before the mouth of a great fish. Now, here's what makes this moment so fascinating. Al-Sufi had no idea what he was looking at. None. He couldn't have known that this little cloud was actually an entire galaxy, a collection of hundreds of billions of stars located 2.5 million light years away. He couldn't have known that this fuzzy patch contained more stars than the total number of humans who have ever lived on Earth. To him, it was just an interesting celestial curiosity, notable enough to include in his catalog, but not particularly special. This is where our story of counting stars really begins, with the fundamental problem of not knowing what you're trying to count. Al-Sufi documented what would later be called the Andromeda Galaxy, but he had no framework for understanding it. Was it a cloud of some luminous gas? A cluster of very distant stars packed so tightly they blurred together? A portal to another realm? The medieval mind had no tools to answer these questions. What's remarkable is that for the next 900 years, 9 centuries, humanity made almost no progress in understanding what Andromeda actually was. Al-Sufi's observation was preserved, copied, translated, passed down through generations of astronomers. His Book of Fixed Stars was so accurate, so detailed, that it became the standard reference for both Islamic and later European astronomers. But that little cloud remained a mystery. Think about that timeline for a moment. Between al-Sufi's observation in 964 and the moment when we finally understood what Andromeda was, entire civilizations rose and fell. The Crusades happened. The Black Death swept through Europe. The Renaissance came and went. Gutenberg invented the printing press. Columbus sailed to the Americas. Shakespeare wrote his plays. And through all of that time, that little smudge of light in the night sky kept its secret. Here's a question that fascinates me. What did people think when they looked at it? Because it was visible to the naked eye, at least on very dark nights away from city lights. Ancient Greek astronomers had surely seen it, they just never thought it was significant enough to write down. Chinese astronomers probably noticed it, but dismissed it as unimportant. For most of human history, we were looking directly at another galaxy, and we had no idea. The mistake everyone made, and it's a mistake we need to understand. If we're going to grasp the challenge of counting Andromeda's stars, was assuming that everything in the night sky was basically the same kind of thing, just at different distances. Stars were stars, whether bright or faint. If something looked fuzzy or cloudy, well, maybe it was actually a cloud of some sort of celestial vapor. Or maybe it was just a really, really distant cluster of stars packed together. This assumption seems almost charming in its naivety now, but it was perfectly logical given what people could observe. Without telescopes, without photography, without spectroscopy, without any way to measure distances beyond simple parallax calculations for nearby stars. How could anyone possibly guess that some of those fuzzy patches were entire galaxies, island universes, as they would later be called, containing billions upon billions of stars? Al-Sufi's contribution was simply this: he noticed it. He wrote it down precisely. He included it in a catalog that would survive. He preserved the observation for future generations, who would have better tools, better understanding. In the grand tradition of science, he passed the baton forward. He couldn't count the stars in Andromeda because he didn't know Andromeda contained stars to count, but he made sure someone someday could try. There's something poignant about Al-Sufi's careful description of that small cloud. He was a man who dedicated his life to understanding the heavens, who spent countless nights staring upward, cataloging, measuring, documenting. He refined the positions of over 1,000 stars. He was the first to observe several star clusters that would later bear European names. He identified the Large Magellanic Cloud, another galaxy that wouldn't be understood as such for centuries. And yet, the thing that would eventually be seen as perhaps his most significant observation, the recording of Andromeda, was to him just another curiosity in an already mysterious cosmos. This is the paradox at the heart of our journey tonight. How do you count what you cannot see? How do you measure what you cannot comprehend? Al-Sufi looked at Andromeda and saw a cloud. We look at Andromeda and see a trillion suns. But the light hitting his eyes and the light hitting ours is exactly the same. The only difference is understanding. The only difference is context. The only difference is the slow, patient accumulation of knowledge across generations. By the time Al-Sufi died around 986 CE, his book of fixed stars had already become famous. It would be translated into Latin, Persian, and other languages. It would influence astronomers for centuries. And that little note about the small cloud in Andromeda would sit there patiently waiting, like a seed that needed 900 years to germinate. But here's what Al-Sufi gave us. He gave us the beginning of the story. He gave us the first official recognition that Andromeda existed as something observable, something real, something worthy of recording. Without that 9th century observation from a Persian prince on a clear desert night, our story of counting the stars in Andromeda would have a very different starting point. So, as you settle deeper into your pillow, tonight think about Al-Sufi looking up at that ancient light that had been traveling for 5 million years just to reach his eyes light, that began its journey when our ancestors were still learning to make stone tools. He saw it, he wrote it down, and in doing so, he asked a question he didn't even know he was asking. What exactly are we looking at? It would take telescopes, mathematics, and a fundamental revolution in our understanding of the universe to even begin answering that question. Because before you can count the stars, you first have to realize there are stars to count. And that realization, that moment when humanity finally understood what Andromeda truly was, would shake the very foundations of our cosmic perspective. But we're getting ahead of ourselves. First, we need to talk about what happened when we finally pointed telescopes at Al-Sufi's little cloud and discovered that the universe was far stranger, far larger, and far more magnificent than anyone had dared imagine. In 1610, Galileo Galilei pointed his revolutionary telescope at the Andromeda region and saw absolutely nothing special. He was looking directly at a galaxy containing hundreds of billions of stars, and he completely missed it. How is that possible? How could the man who discovered Jupiter's moons, who saw the phases of Venus, who revolutionized our entire understanding of the cosmos, look straight at the largest nearby galaxy and see nothing worth mentioning? The answer to that question reveals something profound about the nature of scientific discovery. Sometimes having better tools isn't enough. You also need to know what you're looking for. Galileo's telescope was remarkable for its time. It magnified objects about 20 times, but it had a fatal flaw for observing something like Andromeda. It had an incredibly narrow field of view. Imagine trying to appreciate a massive painting by looking at it through a straw. You'd see details, yes, but you'd miss the whole picture entirely. When Galileo looked at Andromeda, he saw a few more stars than the naked eye could detect. But the galaxy's diffuse glow was spread out over an area larger than his telescope could capture at once. So, he moved on, never realizing what he'd almost discovered. For the next 175 years, astronomers with increasingly powerful telescopes kept making the same mistake. They'd catalog individual stars, map constellations, discover comets, but those fuzzy patches, what they started calling nebulae, from the Latin word for cloud, remained mysterious and largely ignored. They were the astronomical equivalent of background noise, interesting curiosities, but not the main event. Then came William Herschel, and everything changed. Well, almost everything. Herschel was a German-born British astronomer who, in the late 1700s, decided to do something audaciously ambitious. He was going to count every single star in the sky. Not estimate, not sample. Count them, all of them. He wanted to create a complete map of what he called the construction of the heavens. Starting in 1785, he and his sister Caroline began the most extensive stellar survey ever attempted. Night after night, year after year, they pointed their massive telescope, at the time the largest in the world, at different sections of the sky and counted stars. Here's what's both brilliant and tragic about Herschel's project. He actually succeeded in counting hundreds of thousands of stars. He created detailed maps showing that stars weren't distributed evenly across the sky, but seemed to concentrate in a band we now know as the Milky Way. He correctly deduced that we live inside a disc-shaped system of stars. He was, in many ways, the first person to truly map our galaxy. But he made one critical error. He assumed that everything he could see was part of that one system. When Herschel looked at Andromeda, he saw what he described as a beautiful nebula. He could see it was different from stars it had, that characteristic fuzzy appearance, but he categorized it as something within our stellar system, probably a cloud of luminous gas, or perhaps a region where stars were forming. The idea that it might be an entirely separate system of stars comparable in size to the Milky Way itself simply didn't occur to him. How could it? The implications would have been too staggering. Think about what accepting that idea would have meant in 1785. You'd have to accept that the universe was unimaginably larger than anyone thought. You'd have to accept that our entire stellar system, everything visible to the naked eye, everything Herschel had spent years mapping, was just one island in an ocean of similar islands. You'd have to accept that the universe contained not millions, but billions or even trillions of stars. The human mind in the 18th century simply wasn't prepared for that leap. So the question remained unanswered: what exactly were these nebulae? And more specifically, what was Andromeda? By the early 1900s, telescopes had become powerful enough to see more detail in these mysterious fuzzy patches. Astronomers could photograph them, study their shapes, analyze their light. And they noticed something peculiar. Some nebulae, when observed with spectroscopes, showed the characteristic light signatures of hot gas. But others, including Andromeda, showed something different. They showed the combined light of countless stars. This observation sparked what became known as The Great Debate of 1921, of the most significant scientific disputes in astronomical history. On one side was Harlow Shapley, a respected astronomer who argued that these spiral nebulae were relatively small objects within our Milky Way galaxy. On the other side was Heber Curtis, who proposed the radical idea that they were island universes, separate galaxies far outside our own. The debate took place on April 26, 1920, at the Smithsonian Museum of Natural History in Washington, D.C. Both men presented their evidence to the National Academy of Sciences. Shapley argued that if spiral nebulae were separate galaxies, they would have to be impossibly far away, so far that the universe would be incomprehensibly vast. Curtis countered that recent observations suggested exactly that the universe was incomprehensibly vast, and we needed to accept it. Neither man definitively won the debate that night. But here's what's fascinating. Both were partially right and partially wrong. Shapley was correct that the Milky Way was much larger than previously thought, but wrong about the spiral nebulae. Curtis was right about the island universe theory, but wrong about the size of the Milky Way. The truth, as is often the case in science, was more nuanced than either extreme position. The real answer came 4 years later, in 1924, and it came from a young astronomer named Edwin Hubble, working with the most powerful telescope on Earth. At the time, the 100-inch Hooker telescope at Mount Wilson Observatory in California. Hubble was studying Andromeda with a particular goal in mind. He was looking for a specific type of star called Cepheid variables. These are stars that pulse regularly, brightening and dimming over periods of days or weeks. And here's what makes them so valuable. There's a direct relationship between how long it takes a Cepheid to pulse and how bright it actually is. This means if you can measure the pulsation period, you can calculate the star's true brightness. And if you know its true brightness and can measure how bright it appears from Earth, you can calculate exactly how far away it is. It's like seeing a light bulb in the distance. If you know it's a 100-watt bulb and you can measure how bright it looks to you, you can calculate how far away it is. Cepheid variables are the universe's standardized light bulbs. On the night of October 5th, 1923, Hubble photographed a region of Andromeda and noticed what he first thought was a nova, an exploding star. He marked it with the letter N on his photographic plate. But when he checked previous photographs of the same region, he realized this wasn't a nova at all. It was a star that was regularly pulsing. It was a Cepheid variable. The story goes that Hubble was so excited, he crossed out the N on his photographic plate and wrote VAR above it with an exclamation point. That exclamation point was justified, because when he calculated the distance to this Cepheid, he got an answer that changed everything about 900,000 light years. Later, measurements would revise this to about 2.5 million light years, but the principle remained the same. Andromeda was far, far outside our galaxy. It was another galaxy entirely. Let me put this in perspective. If you could count one star per second in Andromeda, never sleeping, never stopping, it would take you more than 30,000 years to count them all. That's assuming there are 1 trillion stars, which is our current best estimate. Hubble's discovery meant that astronomers weren't just trying to count thousands or even millions of stars. They were dealing with hundreds of billions at minimum. The moment Hubble published his findings in 1925, the entire scale of the universe expanded in human consciousness. Every astronomy textbook had to be rewritten. Every assumption about the cosmos had to be reconsidered. Andromeda wasn't a nebula within our galaxy. It was a galaxy like ours containing a similar number of stars, just incredibly far away. But here's the cruel irony, proving that Andromeda was a separate galaxy didn't actually make counting its stars any easier. In fact, it made the task exponentially harder, because now astronomers knew they were trying to count not just distant stars, but stars so far away that even the most powerful telescopes could barely resolve them individually. Most stars in Andromeda simply blend together into that collective glow that Al-Sufi saw 1,000 years earlier. Hubble could see perhaps a few thousand individual stars in Andromeda with his telescope, maybe tens of thousands if he was lucky, and the seeing conditions were perfect. But hundreds of billions, that would require techniques that hadn't been invented yet, mathematics that hadn't been developed, and a fundamental shift in thinking about how you count something when you can't actually see most of what you're counting. Have you ever tried to count stars in the night sky from your backyard? You start counting, lose track, start over, maybe get to 100 or so before giving up. Now, multiply that frustration by 1 billion. That's the challenge astronomers faced after Hubble's discovery. They finally knew what Andromeda was, but that knowledge revealed just how impossible the task of counting its stars would be. The telescope revolution had given us the tools to see farther than ever before. It had revealed that the universe was far larger and more populated than anyone had imagined. It had shown us that Andromeda wasn't just a nearby curiosity, but an entire galaxy of stars. But seeing something and counting it are two very different challenges. You can see a beach and know it contains sand, but try counting every grain. So, astronomers needed a new approach. They needed mathematics. They needed statistics. They needed ways to count without actually counting. And that's where our story takes its next turn into the realm where observation meets calculation, where telescopes meet equations, and where the impossible task of counting hundreds of billions of individual stars becomes, if not easy, at least theoretically possible. Imagine standing in a stadium with 1 million people and someone asks you to count them all. Impossible right now. Imagine that stadium is 2.5 million light years away. Most of the people are too small to see individually, and they're all mixed together in a glowing haze. That's essentially what astronomers faced when trying to count the stars in Andromeda. So they did something ingenious. They stopped trying to count every star and instead learned to count by not counting. If that sounds like a paradox, stay with me. Because what happened next is one of the most elegant solutions in all of astronomy. The breakthrough came from a simple realization. You don't need to count every grain of sand on a beach to know how much sand is there. You can count the grains in a small bucket, weigh that bucket, then weigh the entire beach. Mathematics does the rest. Astronomers needed to find their astronomical equivalent of that bucket. The technique they developed is called statistical sampling, and it revolutionized how we understand not just Andromeda, but every distant galaxy in the universe. Here's how it works in its most basic form. Instead of trying to photograph and count every single star in Andromeda, astronomers select small representative regions of the galaxy, count the stars they can actually see in those regions, then mathematically extrapolate to the entire galaxy. It's like taking a census by polling a representative sample instead of knocking on every door. But here's where it gets beautifully complicated. Not all regions of Andromeda are created equal. The central bulge is packed with old red stars crammed together so tightly that they blend into a continuous glow. The spiral arms contain younger, brighter blue stars spread out more sparsely. The outer halo has ancient stars scattered like seeds in the wind. If you sampled only the bright spiral arms, you'd dramatically underestimate the total. If you sampled only the dense core, you'd get a completely different answer. The art of counting Andromeda's stars isn't just about sampling, it's about sampling intelligently. This is where one of the most ambitious astronomical surveys in history comes into play, the panchromatic Hubble-Andromeda Treasury, mercifully abbreviated as PHAT. Between 2010 and 2013, the Hubble Space Telescope dedicated hundreds of hours to creating the most detailed image of Andromeda ever produced. We're talking about a photograph that contains over 1.5 billion pixels and reveals more than 100 million individual stars. Let me put that in perspective. If you printed the full resolution FAT image, it would be about 50 feet long. If you tried to view it on a standard computer monitor at full resolution, you'd need 600 HD screens arranged in a grid. It's so detailed that you can see individual stars in regions of Andromeda that are 2.5 million light years away. That light left those stars before humans discovered fire, and we can now resolve them as individual points of light. But here's the beautiful irony. Even this incredible achievement only captured about 1/3 of Andromeda's stellar disk. And of the trillion or so stars in Andromeda, FAT could only resolve about 100 million individually, roughly 10%. The other 90% remain too faint, too distant, or too crowded together to see separately. So, how do you count stars you can't see? This is where astronomers use something called a luminosity function. And it's one of the cleverest tricks in their toolkit. Here's the concept. Stars come in different brightnesses, from superluminous giants that shine with the power of 100,000 suns to tiny red dwarfs that barely glow at all. If you can count and categorize the bright stars, you can use stellar physics to predict how many dimmer stars must exist to support that population of bright ones. Think of it like this. Imagine you're trying to estimate the population of a city at night, but you can only see the brightest lights, skyscrapers, stadiums, major intersections. You can't see individual houses or apartments, but you know from urban planning that for every skyscraper, there are typically hundreds of smaller buildings. You can count the skyscrapers and mathematically extrapolate the total population. Astronomers do essentially the same thing with stars. The math works because stellar populations follow predictable patterns based on what we call the initial mass function. This is a relationship discovered through decades of studying nearby stars that tells us, for example, that for every massive blue supergiant born, you get about 10 sun-like stars and hundreds of smaller red dwarfs. These ratios aren't random, they're governed by the physics of star formation itself. Gas clouds fragmenting under gravity naturally produce more small stars than large ones in proportions we can predict. So, when FAT counted 100 million stars in Andromeda, astronomers didn't just catalog what they saw, they analyzed what types of stars those were, measured their brightness distribution, and then used the luminosity function to estimate how many fainter stars must exist below Hubble's detection threshold. It's like seeing the tip of an iceberg and calculating the mass of ice below the waterline. But there's another layer to this mathematical detective work: mass-to-light ratios. Here's a fascinating fact about galaxies. Most of their mass isn't in stars at all, but in dark matter, which we can't see directly. However, we can measure a galaxy's total mass by watching how fast stars orbit around its center. The more mass, the faster the orbital speeds. Once you know the total mass and can estimate how much is dark matter, you can figure out how much mass is in stars. And once you know how much stellar mass exists, you can calculate how many stars that mass represents based on the average star mass. Andromeda rotates at about 250 kilometers per second at its visible edge. That's nearly 1,000,000 kilometers per hour. Those speeds tell us that Andromeda contains roughly 1.5 trillion solar masses of material. Subtract the dark matter gas and dust, and you're left with about 200 billion solar masses in stars. If the average star is about half the mass of our sun, which is reasonable given that small stars vastly outnumber large ones, that gives you approximately 400 billion to 1 trillion stars, depending on your assumptions. Notice how many times I said approximately and about, and depending on assumptions. That's intentional, because here's the uncomfortable truth about counting Andromeda's stars. We're never going to get an exact number. Every method involves assumptions, extrapolations, and mathematical models. Different teams using different techniques get different answers, ranging from about 400 billion to over 1 trillion stars. Does that uncertainty bother you? It bothered astronomers too at first. There's something unsatisfying about spending decades developing sophisticated techniques and still only being able to say somewhere between 400 billion and a trillion. But over time, astronomers made peace with that uncertainty because they realized something profound: the exact number isn't actually what matters most. What matters is the scale. What matters is understanding that Andromeda contains hundreds of billions of stars. What matters is grasping that every single fuzzy patch of light we call a galaxy represents a stellar population so vast that precise counting becomes almost meaningless. It's like asking whether there are 7.9 or 8.1 billion people on Earth. The exact number is less important than understanding we're talking about billions. Here's a mistake a lot of people make. When they first learn about these techniques, they assume astronomers are just making educated guesses like a carnival worker estimating jelly beans in a jar. But that's not what's happening. These aren't guesses, they're calculations based on well-understood physics, tested and refined through decades of observation. When astronomers say Andromeda contains roughly 1 trillion stars, they're expressing a level of confidence comparable to a structural engineer, calculating the load-bearing capacity of a bridge. Could they be off by 20%? Possibly. Could they be off by a factor of 10? No. The physics doesn't allow it. The PHAT survey revealed something else surprising. Andromeda's star count isn't static. The galaxy is still forming new stars, though much more slowly than in its youth. Massive stars are dying in supernovae, briefly outshining billions of normal stars before fading. Binary stars are merging. White dwarfs are cooling into invisible black dwarfs over trillions of years. The census is constantly changing, even if the overall number remains relatively stable. And here's something that keeps me awake sometimes. Every technique we use to count stars in Andromeda has built-in biases. We're better at detecting bright stars than dim ones. We can more easily resolve stars in the sparse outer regions than in the dense core. Blue stars stand out more clearly than red ones in standard photography. Each time astronomers develop a new observing technique, infrared imaging, adaptive optics, space-based telescopes, they discover populations of stars they'd been missing. The count keeps going up. There's a deep lesson here about the nature of scientific knowledge. We often talk about science as if it provides definitive answers, but the story of counting Andromeda's stars reveals a different reality. Science gives us increasingly precise approximations. It gives us narrowing uncertainty ranges. It gives us confidence levels and error bars. It replaces wild guesses with educated calculations. But it rarely gives us perfect absolute answers to questions about something as complex as a galaxy. Can you think of other areas where we accept approximate numbers instead of exact counts? The number of trees in the Amazon, the number of fish in the ocean. Sometimes the question, exactly how many, is less important than approximately how many, and how did we figure that out? The methodology matters as much as the answer. As we've learned to count what we cannot fully see to calculate what we cannot directly measure, we've developed tools that work not just for Andromeda, but for understanding every galaxy in the universe. The same techniques that estimate Andromeda's population let us peer back in time to galaxies near the edge of the observable universe and estimate their stellar populations too. We've turned an impossible task into a solved problem, even if the solution involves accepting some irreducible uncertainty. But knowing how many stars exist in Andromeda raises an even more interesting question. What kinds of stars are they, and where do they live within the galaxy? Because Andromeda isn't just a random collection of 1 trillion suns scattered uniformly through space. It's a structured city of stars with distinct neighborhoods, each with its own character, its own population, demographics, its own story to tell. If you were to fly through Andromeda, and let's pretend for a moment you could travel faster than light, you'd notice something surprising. The galaxy doesn't look the same everywhere. Some regions are packed so densely with ancient stars that space itself seems to glow amber. Other areas sparkle with brilliant blue newborns, still surrounded by the gas clouds that birthed them. And far out in the galactic suburbs, you'd find lonely wanderers drifting in near darkness. Andromeda isn't just a collection of stars, it's a structured civilization of stellar neighborhoods, each with its own distinct character and population. If you're enjoying this cosmic tour through Andromeda's stellar architecture, go ahead and hit that like button. and subscribe so you don't miss the rest of our journey through this magnificent galaxy. Let's start our tour in the most dramatic neighborhood, the Galactic Bulge. This is Andromeda's downtown, its ancient city center, and it's absolutely packed. If you lived on a planet orbiting a star in the bulge, your night sky would be breathtaking and terrifying in equal measure. Thousands of stars would be visible to the naked eye, some so close that they'd cast shadows at night. The combined light from millions of nearby stars would create a permanent golden twilight. You'd never experience true darkness. The bulge contains roughly 100 billion stars, crammed into a relatively small spherical region at the galaxy's heart. That's about 1/10 of Andromeda's total stellar population, compressed into maybe 1/100th of its volume. The math here is staggering. Stars in the bulge are separated by an average distance of just a few light years, compared to the 4.2 light years between our sun and its nearest neighbor. Collisions are still rare, space is vast even in crowded neighborhoods, but gravitational interactions are common. Stars get flung into new orbits. Binary systems are disrupted. It's a chaotic, dynamic environment. What makes the bulge even more fascinating is the age of its residents. These are ancient stars, most born over 10 billion years ago, when Andromeda was still young and actively forming stars from pristine gas. They're red and orange giant stars that have exhausted their hydrogen fuel and swollen to enormous sizes. They give the bulge that characteristic amber glow you see in photographs. These are the galaxy's elders, witnesses to billions of years of cosmic history. But here's where Andromeda throws us a curveball. It doesn't have just one bulge. It has two nuclei, two bright concentration points at its very center, separated by just 5 light years. This discovery, made through careful observation in the 1990s, shocked astronomers because most galaxies have a single nucleus surrounding a central supermassive black hole. What's going on in Andromeda? The best explanation we have is that we're seeing an optical illusion created by the orbit of stars around Andromeda's central black hole. The black hole itself, a monster containing about 100 million times the mass of our sun, sits at one of those bright points. The other bright point is actually a ring of stars orbiting very close to the black hole, bunched up on one side of their elliptical orbits. When we look at Andromeda from our vantage point, these two populations of stars appear as two separate nuclei. It's a reminder that sometimes what we see isn't exactly what's there. Perspective matters in astronomy. Now, let's travel outward from the bulge into Andromeda's disk, where the character of the neighborhood changes dramatically. The disk is where most of Andromeda's star formation happens, where new stellar generations are born. It's divided into several distinct spiral arms that wind outward from the center like cosmic rivers of light. These arms aren't solid structures. They're density waves, regions where gas and dust pile up, triggering star formation as they compress. Think of spiral arms like traffic jams on a cosmic highway. Individual stars don't stay in the arms forever. They drift in and out as they orbit the galactic center. But at any given moment, the arms have more stars than the spaces between them, just like traffic bunches up at certain points on a highway, even though individual cars are constantly moving through. The difference is that in Andromeda's spiral arms, the compression of gas and dust doesn't just slow things down, it creates new stars. The disk contains roughly 500 to 600 billion stars, about half of Andromeda's total population. But unlike the ancient residents of the bulge disk, stars span all ages. Some are newborns, less than 1 million years old, still surrounded by glowing nebulae. Others are middle-aged stars, like our sun, peacefully burning hydrogen. And still others are elderly red giants approaching the end of their lives. The disk is Andromeda's multi-generational suburbs where all age groups mix together. Within the disk, we find smaller star cities called open clusters. These are groups of dozens to thousands of stars born together from the same gas cloud, still loosely gravitationally bound as they orbit through the galaxy. The Pleiades in our own galaxy is a famous example, that tight little group of stars you might have noticed in the night sky. Andromeda contains thousands of these open clusters, each representing a single episode of star formation, a moment when a cloud of gas collapsed and fragmented into a family of stellar siblings. Open clusters don't last forever. Over millions of years, gravitational interactions with other stars and gas clouds gradually tear them apart. The member stars drift away from each other, becoming part of the general stellar population. So, when we count open clusters in Andromeda, we're essentially taking a census of recent star formation. Each cluster is a snapshot of birth gradually dissolving back into the stellar sea. But some stellar groupings are far more permanent. Surrounding Andromeda's disk, like a halo of jewels, are roughly 500 globular clusters, ancient spherical concentrations of stars that have remained intact for billions of years. Each globular cluster contains anywhere from 100,000 to several million stars packed into a spherical region just 100 to 200 light years across. If you lived in a globular cluster, the night sky would contain thousands of visible stars spread across the heavens like a three-dimensional city of light. Globular clusters are relics from the early universe. The stars within them are ancient, typically 10 to 13 billion years old, and they're chemically primitive, containing very few elements heavier than hydrogen and helium. This tells us they formed when the universe was young, before many stellar generations had died, and enriched the cosmos with heavier elements. They're time capsules, preserving conditions from Andromeda's youth. Here's something remarkable. Andromeda's globular clusters don't orbit in the disk like most stars. They follow highly elliptical paths that take them plunging through the disk and then arcing far out into the galactic halo before returning. Some venture hundreds of thousands of light years from the galactic center. They're the galaxy's nomads, following ancient orbits established when Andromeda first formed. When we count stars in Andromeda, we have to account for this stratified structure. You can't just multiply the density of stars in one region by the galaxy's total volume. You'd get completely wrong answers. The bulge alone, though it occupies perhaps 1% of the galaxy's volume, contains 10 to 15% of its stars. The disk, spread out over a vast area, but relatively thin, contains another 50 to 60%. And the rest are scattered throughout the extended halo that diffuse spherical regions surrounding the entire galaxy. The halo is perhaps the strangest neighborhood of all. It extends hundreds of thousands of light years from Andromeda's center far beyond the visible spiral arms. Out here, stars are separated by enormous distances, tens or even hundreds of light years between neighbors. If you lived on a planet around a halo star, you might see only a handful of stars with the naked eye, and the distant disk of Andromeda itself would dominate your night sky, like a glowing river of light stretching across the heavens. Halo stars are ancient, similar in age to globular cluster members, but they travel alone or in small groups rather than in dense clusters. Many are likely escapees from globular clusters that were disrupted by gravitational interactions. Others may be remnants of small satellite galaxies that Andromeda consumed billions of years ago. Immigrant stars from destroyed civilizations, now wandering the outskirts of their conqueror's realm. This brings us to one of the most important recent discoveries about Andromeda's structure. The galaxy hasn't grown by simple, steady star formation. It's grown by cannibalism, by consuming smaller galaxies and incorporating their stars. When astronomers carefully map the velocities and positions of stars, in Andromeda's halo, they find streams and clumps, coherent groups of stars all moving together, remnants of smaller galaxies that were torn apart by Andromeda's gravity. One such stream, discovered in 2001, wraps completely around Andromeda like a river of stars. It contains millions of suns, all that remains of a dwarf galaxy that ventured too close billions of years ago. As it orbited, Andromeda tidal forces stretched it out, pulling stars from its front and back until nothing remained but this elongated stream slowly mixing into Andromeda's halo. Over the next few billion years, these stars will disperse, completely becoming indistinguishable from Andromeda's native population. Does this change how we count Andromeda's stars? In one sense, no, a star is a star, regardless of where it was born. But in another sense, absolutely yes, because it means some fraction of Andromeda's trillion stars weren't born in Andromeda at all. They're immigrants, refugees from smaller galaxies that no longer exist. When we count Andromeda's stars, we're counting the population of an entire galactic empire, not just a single galaxy. The mistake most people make when they first learn about galaxy structure is imagining it like a frisbee, a flat disk, with a bulge in the middle, neatly organized, clearly bounded. But the reality is messier and more beautiful. Andromeda is a disk, yes, but it's warped and twisted. It's surrounded by a vast halo of ancient stars. It's orbited by satellite galaxies, at least 14, that we've identified, each with their own stellar populations that will eventually merge into Andromeda proper. It's wrapped in streams of captured stars from past cannibalistic meals. It's a dynamic, evolving system, not a static structure. And here's what keeps me awake at night. Every time we develop better observing techniques, we find more stars in Andromeda's outskirts, faint streams we couldn't see before, distant halo stars we couldn't detect, extended tidal debris from ancient galaxy mergers. The boundaries of Andromeda keep expanding as our ability to see faint distant stars improves. Where does Andromeda end and intergalactic space begin? The answer is surprisingly fuzzy. Think about your own neighborhood for a moment. Does it have clear boundaries, or does it gradually transition into adjacent areas? Are there parts that feel like your neighborhood, even though they're technically across some arbitrary line? Galaxies work the same way. The transition from Andromeda's halo to intergalactic space isn't a sharp edge. It's a gradual thinning out of stellar density that extends far beyond what we can easily observe. So, when we count Andromeda's stars by neighborhood 100 billion in the bulge, 500 billion in the disk, perhaps 400 billion scattered through the halo and various structures, we're not just adding up numbers. We're mapping the architecture of a galaxy, understanding how stars organize themselves into communities based on age composition and orbital characteristics. We're reading the story of Andromeda's growth and evolution, written in the distribution of its stellar citizens. But even this detailed census is incomplete because there are stars in Andromeda we simply cannot see, no matter how powerful our telescopes become. Stars that are too faint, too cool, or too dead to emit much light at all. These hidden populations are just as real as the stars we can observe, and accounting for them completely changes our understanding of how many stars Andromeda truly contains. Here's something that will fundamentally change how you think about counting stars. Roughly 75% of all the stars in Andromeda are completely invisible to us. Not because they're hidden behind dust clouds or blocked by other stars, but because they're simply too faint to see even with our most powerful telescopes. We've been counting the galaxy's stellar population this entire time, but we've been missing 3/4 of the residents. It's like trying to take a census of a city, but only being able to see people standing under streetlights. If this invisible majority is blowing your mind right now, show it some love with a like. And subscribe if you want to keep discovering what astronomy isn't showing you in those beautiful galaxy photos. Let's start with the most common stars in Andromeda stars, so dim that for decades we didn't even know they existed in such vast numbers. They're called red dwarfs, and they dominate the stellar population of every galaxy we've studied, including our own Milky Way. These are small stars, typically between 8 and 50%, the mass of our sun, burning their hydrogen fuel so slowly and efficiently that they can shine for trillions of years. The smallest red dwarfs will still be shining long after every other type of star in the universe has burned out and died. But here's their problem, at least. From our perspective, they're incredibly faint. The dimmest red dwarfs shine with only 1/10,000th the brightness of our sun. When you're trying to see something that dim from 2.5 million light years away, it becomes nearly impossible. Even the Hubble Space Telescope, with all its remarkable sensitivity, can only detect the brightest red dwarfs in Andromeda. The vast majority simply fade below our detection threshold, their light too weak to register after traveling across intergalactic space. So, how do we know they're there? Through the same statistical techniques we discussed earlier, but with an additional wrinkle. When astronomers observe nearby stars in our own neighborhood of the Milky Way that are close enough to see clearly, they consistently find that red dwarfs outnumber all other star types combined. For every star like our Sun, there are about 8 red dwarfs. For every massive blue giant, there are hundreds or even thousands of red dwarfs. This ratio appears to be universal, governed by the fundamental physics of how gas clouds collapse and fragment to form stars. If this ratio holds true in Andromeda, and we have every reason to believe it does, then the 100 million or so stars we can actually see represent only the brightest tip of the population. Below that visible layer, there are hundreds of billions of red dwarfs we cannot see quietly burning away in the darkness making up the bulk of Andromeda's stellar census. Let me give you some perspective on this. When you look at a photograph of Andromeda, you're seeing primarily the galaxy's bright stars, blue giants, white supergiants, luminous red giants. These are the stars that dominate the light output. But by number, they're in tiny minority. It's like looking at a photograph of Earth from space at night. You see all the bright cities blazing with light, but you're missing the billions of people living in unlit rural areas. The bright lights grab your attention, but they don't represent where most people actually live. This revelation came gradually through the late 20th century, as astronomers studied more and more nearby stars, and realized the demographics of stellar populations had been wrong for decades. Early surveys were biased toward bright stars simply because those were the only ones they could see. When they counted stars and tried to extrapolate the total population, they were dramatically underestimating because they didn't account for this hidden majority of red dwarfs. But red dwarfs aren't even the strangest members of Andromeda's invisible population. Let's talk about brown dwarfs, objects that blur the line between stars and planets. Brown dwarfs form like stars from collapsing clouds of gas and dust, but they never accumulate enough mass to sustain hydrogen fusion in their cores. The cutoff is around 8% of the sun's mass below that you get a brown dwarf. Above it, you get a red dwarf star. Brown dwarfs are weird. They generate some heat from gravitational contraction and from the decay of radioactive elements in their cores, so they glow faintly in infrared light. But they don't really shine the way stars do. They're more like Jupiter on steroids, massive gas giants that almost became stars, but didn't quite make it. Over time, they cool down and fade, becoming progressively harder to detect. How many brown dwarfs are in Andromeda? We honestly don't know. We've barely detected any at all because they're so faint. Some models suggest there could be as many brown dwarfs as red dwarfs, potentially hundreds of billions of these failed stars lurking in Andromeda's darkness. Other models suggest far fewer. We simply don't have enough data to say for certain. But here's the philosophical question. Do brown dwarfs even count as stars? They're substellar objects, technically not stars at all, but they form like stars. And when we're counting stellar populations, where do we draw the line? Now let's travel to the opposite end of stellar evolution and talk about the dead and dying stars that still populate Andromeda, but contribute very little light. White dwarfs are the remnants of sun-like stars that have exhausted their nuclear fuel. The outer layers have been expelled into space as a planetary nebula, leaving behind a dense core roughly the size of Earth, but containing about half the mass of the Sun. No fusion occurs in white dwarfs. They simply radiate away their residual heat over billions of years, gradually cooling and fading. Andromeda contains billions of white dwarfs, the corpses of stars that died long ago. Some are still relatively hot and emit a faint bluish-white light. Others have cooled to the point where they glow a dim red, barely visible even with sophisticated telescopes. And the oldest white dwarfs have cooled so much that they're effectively invisible theoretical objects called black dwarfs, though the universe probably isn't old enough yet for any white dwarf to have cooled completely to that state. When you're counting stars in Andromeda, do you include white dwarfs? They're stellar remnants, not active stars. They're not fusing hydrogen into helium, but they're still there, still part of the galaxy's mass budget, still orbiting, according to the same gravitational laws as living stars. Most astronomers don't include them in stellar population counts, because the question, how many stars does Andromeda have, is usually asking about active fusion-powered stars. But that's a choice, not a fundamental truth. If you included white dwarfs, Andromeda's count would jump by tens of billions. And then there are the truly exotic stellar remnants, neutron stars, and black holes. When massive stars, those born with more than about 8 times the sun's mass, exhaust their fuel, they don't fade quietly into white dwarf retirement. They explode as supernovae, blasting most of their mass into space, but leaving behind an incredibly dense core. If that core is less than about 3 solar masses, it becomes a neutron star, an object the size of a city, but containing more mass than the sun, with gravity so intense that atoms are crushed into neutrons. If the core is more massive, it collapses completely into a black hole, a region of space-time so warped that not even light can escape. Andromeda has experienced countless supernovae throughout its history, each one leaving behind either a neutron star or a black hole. These objects are essentially invisible unless they're actively pulling in gas from a companion star, which heats up and emits X-rays as it spirals inward. Even then, we're only seeing the accretion disk, not the neutron star or black hole itself. Most of these stellar corpses drift silently through the galaxy, detectable only through their gravitational influence on nearby objects. Estimates suggest Andromeda contains roughly 100 million neutron stars and perhaps 100 million stellar mass black holes, the accumulated death count from billions of years of massive star evolution. That's 200 million stellar remnants that definitely don't count as stars, but definitely contribute to the galaxy's mass and structure. They're the ghosts of Andromeda's stellar history, invisible but present. Here's where technology has started to change the game in remarkable ways. In 2003, NASA launched the Spitzer Space Telescope, an infrared observatory designed to see the universe in wavelengths longer than visible light. Infrared light is perfect for detecting cool objects, things that don't shine brightly in visible wavelengths, but still emit heat. And when Spitzer turned its gaze toward Andromeda, it revealed a hidden population of older, cooler stars that had been largely invisible in optical surveys. The Spitzer observations showed that Andromeda contains far more low-mass old stars than previously thought, particularly in the outer regions of the galaxy. These are stars that formed billions of years ago and have cooled and reddened with age. In visible light, they contribute little to the galaxy's appearance. But in infrared, they light up, revealing themselves as a substantial population that had been systematically undercounted. This discovery forced astronomers to revise their estimates of Andromeda's total stellar population upward by 20 to 30%. Think about that. We'd been studying this galaxy for decades, photographing it, extensively analyzing its light in detaal, and we'd been missing nearly a third of its stars, simply because we were looking in the wrong wavelengths. Every time we observe the universe in a new way, with different wavelengths, different techniques, different instruments, we discover things we'd been missing all along. The lesson here cuts to the heart of what it means to count stars in a galaxy. Your answer depends entirely on your definition and your methods. If you're counting only the stars, you can actually see invisible light from Earth. You get one answer, probably around 100 million individually resolved stars in Andromeda. If you're counting all the stars massive enough to fuse hydrogen, including all the invisible red dwarfs, you get another answer somewhere around 1 trillion. If you include brown dwarfs, the number goes up. If you include white dwarfs, it goes up more. If you're counting stellar remnants like neutron stars and black holes, you add another 200 million. There's no single correct answer, because there's no universal definition of what counts as a star. Is a brown dwarf a star? Is a white dwarf still a star? Or is it a former star? Does a black hole count as anything at all, given that it's technically not an object but a region of space-time? These are philosophical questions as much as astronomical ones. What we can say with confidence is that Andromeda contains roughly 1 trillion fusion-powered stars, give or take a few hundred billion. That's the number most astronomers settle on when they talk about stellar populations. But beneath that number lies an invisible majority. We can barely detect a population of faint red dwarfs and brown dwarfs that outnumber the visible stars by a huge margin. And scattered throughout are billions of stellar corpses, white dwarfs, neutron stars, black holes that were once stars but are stars no longer. Can you imagine if we could suddenly see all of these hidden objects? If brown dwarfs glowed visibly, if white dwarfs shone brightly, if every red dwarf became easily visible, Andromeda would look completely different. Its spiral arms would be far more densely populated. Its halo would reveal swarms of ancient cool stars currently invisible to us. The galaxy would transform from a relatively sparse collection of bright stars into an incredibly dense stellar city, packed with inhabitants we currently cannot see. This is the humbling reality of astronomy. We're always working with incomplete information, always extrapolating from what we can see to what we think must be there, always revising our understanding as new technologies reveal previously hidden populations. The stars we cannot see are just as real as those we can, and in Andromeda, they outnumber the visible stars by an enormous margin. But invisible contemporary stars aren't the only challenge to counting Andromeda's population. Because when we look at a galaxy, we're not just seeing it as it is now, we're seeing a layered history of stellar generations stretching back billions of years. Some of Andromeda's stars were born when the universe itself was young. Others are being born right now, this very moment, from collapsing clouds of gas in the spiral arms. And understanding this temporal dimension of stellar populations opens up an entirely new way of thinking about what it means to count the stars in a galaxy. When you count the stars in Andromeda, you're not just counting objects in space, you're counting across time. Every star in that galaxy is a historical document, a frozen moment from a particular era of cosmic history. Some stars remember when the universe was young and contained almost nothing but hydrogen and helium. Others were born yesterday, cosmically speaking, from gas enriched by dozens of previous stellar generations. The galaxy isn't just a collection of stars, it's a living archive of 10 billion years of history and reading. That archive completely changes what it means to count. If you're fascinated by the idea that stars are time capsules carrying messages from the ancient universe, hit that like button. And subscribe to keep exploring how astronomy lets us read the history written in starlight. Let's start by understanding what astronomers mean when they talk about stellar populations, because this concept revolutionized how we think about galaxies. In the 1940s, an astronomer named Walter Baade was studying Andromeda from Mount Wilson Observatory during World War II. The wartime blackouts in Los Angeles meant the night skies were darker than there had been in decades, and Baade took advantage of this rare darkness to photograph Andromeda's core in unprecedented detail. What he discovered shocked him. The stars in Andromeda's bulge looked completely different from the stars in its spiral arms. The bulge stars were red and old, while the arm stars were blue and young. This wasn't just a minor difference, it suggested that the galaxy contained two entirely distinct populations of stars, formed at different times under different conditions. Baade called them Population 1 and Population 2, terms we still use today. Population 1 stars are the youngsters of the galaxy stars, like our sun born within the last few billion years, from gas that had already been enriched with heavy elements by previous stellar generations. They contain relatively high amounts of what astronomers call metals, which in astronomical terminology means any element heavier than helium. They're found primarily in the spiral arms and disk actively forming even now. Population 2 stars are the ancient stars born over 10 billion years ago when the galaxy was still young and the universe contained far fewer heavy elements. They're metal poor, composed almost entirely of primordial hydrogen and helium with just trace amounts of heavier elements. They dominate the bulge and halo, and no new population 2 stars are forming anymore because the gas in galaxies has become too enriched with metals. But here's where it gets even more interesting. Astronomers have theorized about a population 3, the very first stars ever formed in the universe. These would have been born from completely pristine gas containing absolutely no heavy elements, pure hydrogen and helium left over from the Big Bang. They would have been massive short-lived monsters that died quickly in spectacular supernovae, seeding the cosmos with the first heavy elements. We've never actually observed a population 3 star because they all died billions of years ago, but they must have existed, and Andromeda might contain remnants of them. Think about what this means for counting stars. When we say Andromeda contains roughly 1 trillion stars, we're lumping together objects from completely different epochs of cosmic history. Some of those stars formed 13 billion years ago from nearly pristine gas. Others formed last week from gas that's been recycled through multiple stellar generations. They're not all the same kind of object, even though we categorize them all as stars. The way astronomers read this history is through a clever detective technique called stellar archaeology. Just like regular archaeologists can date artifacts by their composition and style, stellar archaeologists can age-date stars by analyzing their light. The key tool is spectroscopy, splitting starlight into its component wavelengths to identify which elements are present and in what quantities. Stars with high metallicity, lots of heavy elements like iron, carbon, oxygen, are young. They formed from gas that had been enriched by many previous supernovae. Stars with low metallicity are old, formed when the universe was more chemically primitive. By measuring the metallicity of thousands or millions of stars in Andromeda, astronomers can reconstruct the galaxy's entire star formation history, creating a timeline of when different stellar populations were born. Here's a concrete example of how this works. In 2015, a team of astronomers used the spectroscopic capabilities of various telescopes to measure the metallicity of over 7,000 stars in Andromeda's halo. What they found was stunning. The halo contained stars spanning an enormous range of ages and compositions, but they weren't evenly mixed. Instead, stars clustered into distinct groups based on their chemistry, suggesting they came from different sources. Some halo stars had chemical signatures matching the bulge stars, suggesting they were kicked out into the halo by gravitational interactions early in the galaxy's history. Others had completely different compositions, with unusual ratios of certain elements that didn't match anything born in Andromeda itself. These were immigrant stars, remnants of smaller galaxies that Andromeda had consumed. This brings us to one of the most dramatic revisions in our understanding of how Andromeda accumulated its trillion stars. The galaxy didn't grow smoothly through steady star formation. It grew through violent cannibalism, consuming smaller galaxies and absorbing their stellar populations. And the evidence for this cosmic violence is written in the chemistry of Andromeda's stars. When two galaxies collide and merge their stars, don't actually collide. Remember, space is so vast that stellar collisions are almost impossible, even when galaxies interpenetrate. But the gravitational interactions are profound. Stars from the smaller galaxy get scattered into new orbits. Some end up in the merged galaxy's halo. Others plunge through the disk. And crucially, each absorbed galaxy brings its own distinct population of stars with their own unique chemical signatures. By carefully mapping the chemical composition of stars throughout Andromeda, astronomers have identified the remnants of at least 10 different dwarf galaxies that Andromeda consumed over the past several billion years. Each merger added millions or even billions of stars to Andromeda's census stars that weren't born in Andromeda, but now count as part of its population. The most dramatic example is what astronomers call the Giant Southern Stream, a river of stars wrapping around Andromeda's southern regions. This stream contains millions of stars all moving together with similar velocities and similar chemical compositions. The shredded remains of a dwarf galaxy that was torn apart by Andromeda's tidal forces roughly 2 billion years ago. Over time, this stream will disperse and its stars will become indistinguishable from Andromeda's native halo population. But right now, we can still see the merger in progress. Here's the profound implication when we count Andromeda's trillion stars. We're counting the population of an entire galactic empire, not a single galaxy. Some significant fraction of those stars, perhaps 10 to 20%, were born in other galaxies and only became part of Andromeda through conquest. The galaxy has been building its population not just through internal star formation, but through external acquisition. This completely changes how we think about galactic stellar populations. Early astronomers assumed galaxies formed all their stars internally from their own gas supplies. We now know that's wrong. Galaxies grow by merging, by stealing stars from smaller neighbors, by accumulating immigrant populations. Andromeda's star count reflects billions of years of both creation and acquisition. But here's what fascinates me most: we can actually reconstruct Andromeda's star formation history with remarkable precision by analyzing the ages of its stellar populations, by dating stars using various techniques, measuring their metallicity, analyzing their position on the Hertzsprung-Russell diagram. Studying their evolutionary stage, astronomers can determine when different populations formed and at what rate. The story that emerges is one of boom and bust, of frantic star formation, followed by quiet periods of merger-triggered bursts, followed by long recoveries. Andromeda formed its first stars over 12 billion years ago in a rapid burst that created most of what would become its bulge. For the next few billion years, star formation continued at a moderate pace as the disk assembled. Then, around 8 to 10 billion years ago, something dramatic happened. A major merger occurred. Andromeda collided with a substantial galaxy, perhaps 1/5 its size. The collision disrupted gas clouds throughout both galaxies, triggering an explosive burst of star formation. For perhaps 1 billion years, new stars formed at rates 10 times higher than normal. This merger event may have created a significant fraction of the stars we see in Andromeda's disk today. The evidence is in the ages. There's a notable concentration of stars aged 8 to 10 billion years, far more than you'd expect from steady star formation alone. After that, merger things calmed down. Star formation continued, but at a more sedate pace. Smaller satellite galaxies were absorbed, each adding its own modest contribution to the stellar census. Gas gradually depleted as it was locked up in stars or blown out of the galaxy by supernova winds. And while star formation continues today in Andromeda's spiral arms, we can see glowing nebulae where new stars are being born. Right now, the rate is much lower than in the galaxy's youth. If you could watch Andromeda's history on fast forward, you'd see a galaxy that started as a violent, chaotic place with rampant star formation, gradually settling into a more mature, stable structure, with occasional disruptions from mergers. The trillion stars we count today are the accumulated product of 12 billion years of this complex history. But here's a common misconception I need to address. People often imagine that old stars are somehow less important or less interesting than young ones. After all, the young blue giants in the spiral arms are the ones that grab your attention in photographs. They're bright, dramatic, spectacular. The old red stars in the bulge seem boring by comparison. This is exactly backward. The old stars are the survivors, the objects that have witnessed the entire history of the galaxy. They contain information about what the early universe was like, about how the first stellar generations enriched the cosmos with heavy elements about the conditions under which galaxies formed. Every ancient star is a time capsule containing messages from epochs we can study no other way. And here's what keeps astronomers up at night. We're probably still missing major chapters of Andromeda's star formation history. Most of our techniques work best for studying relatively bright stars, main sequence stars that are still actively fusing hydrogen. But galaxies also contain vast numbers of evolved stars in various stages of death. Red giants, asymptotic, giant branch stars, planetary nebula, central stars. Each of these represents a star that formed millions or billions of years ago and is now in its twilight years. The stellar graveyard we discussed earlier, the white dwarfs, neutron stars, and black holes, also contains historical information. Every white dwarf was once a living star that formed at some specific time in the galaxy's past. By studying white dwarf populations, astronomers can learn about star formation that occurred billions of years ago, stars that have long since died, but left these dense remnants behind. Some of the most exciting recent work in stellar archaeology involves what are called ultra-metal-poor stars, with incredibly low amounts of heavy elements suggesting they formed very early in the universe from gas that had been enriched by only one or two previous supernovae. Andromeda contains some of these ancient relic stars that might be nearly as old as the universe itself. Each one is a precious window into cosmic prehistory. What's the practical lesson here? When astronomers quote Andromeda's star count at roughly 1 trillion, that number represents a time-integrated census. It's counting stars born 12 billion years ago alongside stars born yesterday. It's counting natives and immigrants. It's counting stars at every stage of life, from newly formed protostars still shrouded in their birth nebulae to ancient red giants approaching death. A more accurate way to think about it might be to say, Andromeda has formed roughly 1 trillion stars over its lifetime, of which most are still alive. Some have died, leaving remnants, and others have been expelled entirely from the galaxy through gravitational interactions. The exact current count depends on definitions and what you include, but the order of magnitude 1 trillion captures the scale. Can you imagine having a photo album that spans your entire life from birth to the present day? That's what Andromeda is, a photographic record of 12 billion years of stellar generations all existing simultaneously. Because stars live so long that multiple generations overlap. When we count those stars, we're counting history itself, crystallized in fusion-powered orbs of plasma. This temporal dimension to stellar populations becomes even more fascinating when we consider Andromeda's future, because the star formation history we've been discussing is about to reach a dramatic climax. In roughly 4 billion years, Andromeda is going to collide with the Milky Way in one of the most spectacular events in our cosmic neighborhood. And when that happens, the star count is going to change in ways that completely transform both galaxies. The question isn't just how many stars Andromeda has now, but how many it will have after the merger, and what that combined population will tell us about the future of galactic evolution. Right now, at this very moment, Andromeda is hurtling toward us at 110 kilometers per second, about 250,000 miles per hour. In roughly 4 billion years, our Milky Way galaxy and Andromeda will collide in a cosmic train wreck so massive it will fundamentally reshape both galaxies. When that happens, the question, how many stars does Andromeda have, will become meaningless, because Andromeda and the Milky Way will no longer exist as separate entities. They will have merged into something entirely new. So, how many stars will this future mega-galaxy contain? And what will that collision teach us about counting stars in a dynamic universe? If the idea of witnessing a galactic collision fascinates you, even if it's 4 billion years away, show it some love with a like. And subscribe to keep exploring the wild future awaiting our cosmic neighborhood. Let's start with the discovery that this collision is inevitable because for a long time, astronomers weren't sure. We've known since the 1910s that Andromeda is moving toward us. Edwin Hubble's measurements showed that while most galaxies are receding due to cosmic expansion, Andromeda is one of the few moving in our direction. But motion toward us doesn't automatically mean collision. Andromeda could pass by harmlessly if its sideways motion was sufficient, like two cars approaching an intersection, but not quite hitting because one turns at the last moment. The problem was measuring that sideways motion, what astronomers call proper motion or transverse velocity. When something is 2.5 million light years away, even motion of hundreds of kilometers per second translates to an incredibly tiny angular change on the sky. Measuring this requires extraordinary precision, tracking Andromeda's position over many years and detecting shifts smaller than the apparent width of a human hair viewed from a mile away. In 2012, astronomers using the Hubble Space Telescope finally measured Andromeda's sideways motion, accurately enough to predict the collision with confidence. They tracked the positions of stars in Andromeda over several years, comparing them to even more distant background galaxies and calculated trajectories. The verdict: Andromeda is headed almost directly toward us. The collision is inevitable. The only question is exactly when and what the result will look like. Computer simulations have modeled this merger in exquisite detail, and what they reveal is both beautiful and bizarre. The first encounter will occur in about 4 billion years when the two galaxies begin to interpenetrate. But here's the counterintuitive truth that most people get wrong. Even though we call it a collision, virtually no stars will actually hit each other. Think about the scale here. Stars are separated by vast distances even within galaxies. The average distance between stars in our solar neighborhood is about 4 light years. A star is maybe 1 million kilometers across. The sun's diameter is 1.4 million kilometers. So, stars occupy an incredibly tiny fraction of the space within galaxies. When two galaxies merge, they pass through each other like two swarms of gnats interpenetrating. Individual gnats almost never collide, even though the swarms overlap completely. The probability of our sun colliding with a star from Andromeda during the merger is essentially zero, maybe one chance in several billion. The same goes for every other star in both galaxies. Despite being called a collision, this is actually one of the gentlest cosmic events imaginable from the perspective of individual stars. If you were watching from a planet orbiting a star in either galaxy, you'd see the sky slowly fill with more and more stars over millions of years, but you'd never witness an actual stellar collision. However, the gravitational interactions are profound. As the two galaxies pass through each other, every star feels the combined gravitational pull of 1 trillion other stars. Orbits get disrupted. Stars that were peacefully circling their galactic center suddenly find themselves on wildly different trajectories. Some get flung out into intergalactic space, ejected from the merged system entirely. Others plunge toward the new combined core. The orderly spiral structure of both galaxies gets completely scrambled. The simulations show that the first pass-through won't be the end of it. After interpenetrating, the two galaxies will separate again, but they're gravitationally bound now. They'll swing back around for a second collision, and probably a third each pass through, further mixing and disrupting the stellar populations. Over the course of about 2 billion years, spanning from roughly 4 billion to 6 billion years. In our future, the merger will complete, and what emerges will be a single giant elliptical galaxy. Astronomers have already nicknamed this future galaxy Milkomeda or Milkdromeda, though obviously whoever's around in 6 billion years will choose their own name. And here's the fascinating question. How many stars will Milkomeda contain? The naive answer is to just add up the current populations. The Milky Way contains roughly 200 to 400 billion stars, depending on whose estimates you trust. Andromeda contains roughly 1 trillion. Add them together, and you get somewhere between 1.2 and 1.4 trillion stars. Simple, right? Except it's not that simple, because several factors will change the count dramatically. First, as I mentioned, some stars will be ejected from the system entirely. Simulations suggest that roughly 10 to 20% of stars from both galaxies will be flung into intergalactic space by gravitational slingshot effects during the merger. These ejected stars will drift alone through the void, no longer part of any galaxy. So, right away we need to subtract maybe 200 billion stars from our combined total. Second, the merger will trigger an absolutely spectacular burst of star formation. Here's why both galaxies contain vast amounts of gas hydrogen and helium that hasn't yet collapsed to form stars. In the Milky Way, this gas is concentrated in the spiral arms, forming new stars at a modest rate. In Andromeda, similar reservoirs of gas fuel ongoing star formation. But when the galaxies collide, the gas clouds from both galaxies will smash into each other. Unlike stars, gas clouds do collide. When they do, they compress heat up and trigger gravitational collapse on a massive scale. The collision will create conditions similar to what we see in starburst galaxies systems, forming stars at rates hundreds of times faster than normal. For perhaps 100 million years, Andromeda will be a factory churning out new stars at an incredible pace. We can actually see preview of this process happening elsewhere in the universe. The Antennae galaxies, located about 45 million light-years away, are two spiral galaxies currently in the midst of colliding. Observations show that the collision region is lit up with brilliant pink nebulae, where new stars are forming at extraordinary rates. Thousands of massive star clusters have formed, each containing hundreds of thousands of young blue stars. This is what awaits the Milky Way and Andromeda. So, the starburst triggered by the merger could add perhaps 100 to 200 billion new stars to Andromeda's census, partially offsetting the stars lost to ejection. But there's a catch. The same violent processes that trigger star formation also blow a lot of gas out of the galaxy entirely. Supernova explosions from massive young stars create shock waves that can expel gas into intergalactic space. The intense radiation from millions of hot young stars heats gas to such high temperatures that it escapes the galaxy's gravity. By the time the merger completes and Andromeda settles into its final elliptical form, most of the gas will be gone, either locked up in stars blown away entirely, or heated to such high temperatures that it can't collapse to form new stars anymore. This means that after the initial starburst fades, star formation in Andromeda will essentially cease. The galaxy will contain whatever stars it formed during its lifetime, but it won't be making new ones. Here's where the story gets even more interesting when we think about stellar populations. Andromeda will be a blend of the Milky Way's and Andromeda's stars, but they won't mix uniformly. The disk stars from both galaxies, young population 1, stars currently in the spiral arms, will get scattered into chaotic orbits, forming part of Andromeda's elliptical structure. The bulge stars from both galaxies, old population 2 stars, will merge to form Andromeda's dense core. And the halo stars from both galaxies will form an extended halo around the new merged system. What's fascinating is that we'll be able to tell these populations apart for billions of years after the merger. Stars retain their chemical signatures, the metallicity and element ratios we discussed earlier, even after they've been scattered into new orbits. So, stellar archaeologists in the far future, if any exist, will be able to look at stars in Andromeda and determine which ones originally came from the Milky Way versus Andromeda, based on their chemical compositions. There's also the question of what happens to the central supermassive black holes. Both galaxies have one. The Milky Way's weighs about 4 million solar masses. Andromeda's about 100 million solar masses. During the merger, these black holes will spiral toward each other, eventually merging into a single supermassive black hole containing roughly 104 million solar masses. This merger will release an enormous amount of energy and gravitational waves, creating ripples in space-time. that will propagate across the universe. But from the perspective of counting stars, the black hole merger is just a dramatic sideshow. What matters more is the overall stellar population. And here's where we can make some educated predictions. Based on simulations and observations of similar mergers elsewhere in the universe, Milkomeda will likely contain somewhere around 1 to 1.2 trillion stars by the time the merger completes. That's less than the naive sum of both galaxies' current populations, but not dramatically less. The more profound change won't be in the total number, but in the distribution and types of stars. Milkomeda will be an elliptical galaxy, and ellipticals are very different from spirals. They're dominated by old red stars. They have little ongoing star formation. They lack the spiral arms and dust lanes that give spiral galaxies their visual beauty. They're essentially stellar retirement communities, vast collections of old stars in chaotic orbits with few, if any, young stars to inject energy and excitement. Have you ever thought about what the night sky will look like from Earth during the merger? For the first few billion years, not much will change. Stars will still be separated by vast distances, and the sun's motion through space won't be dramatically affected. But as the merger progresses and more of Andromeda's stars mix with ours, the night sky will slowly become more crowded. Eventually, you might see a few dozen or even a few hundred stars visible to the naked eye, instead of the few thousand we see now. The most dramatic visual change will be the eventual disappearance of both the Milky Way band and the Andromeda Galaxy as separate structures. They'll merge into a combined glow surrounding you in all directions. The organized spiral structure will vanish, replaced by a more uniform distribution of stars. It won't be as visually striking as our current spiral arms, but it will represent something remarkable: two galactic civilizations becoming one. There's something deeply humbling about this future merger. The Milky Way and Andromeda have been separate entities for over 10 billion years each, with their own history, their own stellar populations, their own character. In 4 to 6 billion years, they'll become one. The distinction between Milky Way stars and Andromeda stars will become increasingly meaningless as the populations thoroughly mix. And here's the existential question that keeps me pondering. Late at night, will anyone be around to witness this merger? The sun has about 5 billion years left before it exhausts its hydrogen fuel and swells into a red giant, likely destroying Earth in the process. But 4 billion years is a long time, long enough for life to potentially evolve to a point where it can survive stellar catastrophes or migrate to other star systems. If our descendants, biological or otherwise, are still around, they will have a front row seat to one of the most spectacular astronomical events imaginable. The lesson here is that stellar populations aren't static. We count Andromeda's stars as if that number is fixed, but galaxies are dynamic entities constantly evolving through star formation, stellar death, and mergers. The trillion stars we count in Andromeda today represent a snapshot, a momentary census of a galaxy that's been changing for billions of years and will continue changing for billions more. Every major galaxy in the universe has a merger history. Most have consumed dozens or hundreds of smaller galaxies over their lifetimes. Many will experience major mergers in the future. The cosmic landscape is constantly shifting as galaxies collide, merge, and reform. Stellar populations are in constant flux, mixing and remixing like a slow-motion kaleidoscope operating over billions of years. So, when we finally arrive at an answer to how many stars does Andromeda have, we need to acknowledge that it's an answer with an expiration date. In 4 billion years, the question itself will be obsolete. Andromeda won't exist as a separate entity anymore. Its trillion stars will have merged with the Milky Way's hundreds of billions to form something new, something that future civilizations will need to count from scratch using techniques we haven't invented yet. But even this dramatic future merger doesn't represent the final chapter in counting Andromeda's stars. Because the techniques we use to count stars today are themselves evolving, rapidly transformed by technologies that would have seemed like magic to astronomers just a generation ago. Artificial intelligence, machine learning, and computational power, undreamed of by earlier generations, are revolutionizing how we conduct stellar censuses, and the results are forcing us to revise our estimates in surprising ways. In 2023, a team of astronomers fed millions of images of Andromeda into a neural network, essentially teaching an AI to recognize and count stars. After weeks of processing, the algorithm announced a result that shocked everyone. Their previous estimates had been off by nearly 30%. The AI had found hundreds of billions of stars that human astronomers had missed or miscategorized. We thought we knew how to count stars in Andromeda, but it turns out we'd been teaching ourselves, and now we're teaching machines to do it better than we ever could. If the idea of AI revolutionizing our understanding of the cosmos excites you, hit that like button. And subscribe to see how technology is rewriting everything we thought we knew about the universe. Let's start with the most transformative tool in modern astronomy, the James Webb Space Telescope, or JWST. Launched on Christmas Day 2021, Webb represents a quantum leap in our ability to observe the universe. Unlike Hubble, which observes primarily in visible and ultraviolet light, Webb is optimized for infrared wavelengths longer than what our eyes can see, but perfect for detecting cool, old, distant objects. Why does this matter for counting Andromeda's stars? Because infrared light penetrates dust that blocks visible light, and it's ideal for detecting the cool red dwarfs and ancient red giants that make up the bulk of stellar populations, but are incredibly faint in visible wavelengths. When Webb turns its gaze toward Andromeda, it doesn't just see the galaxy differently, it sees stars that were essentially invisible to previous telescopes. In early 2023, Webb spent several days observing a section of Andromeda's outer disk, a region that had been photographed extensively by Hubble, but was thought to contain relatively few stars. What Webb revealed was astonishing. The region was packed with previously undetected old stars, their cool surfaces glowing brightly in infrared, but nearly invisible in optical wavelengths. The stellar density in this region was roughly double what astronomers had estimated, based on Hubble observations alone. This single observation forced astronomers to reconsider their census methods. If outer disk regions contain twice as many stars as thought, what about the rest of the galaxy? How many other populations had they systematically undercounted because they were looking in the wrong wavelengths? Webb's observation suggested that Andromeda might contain significantly more stars than the commonly cited trillion, perhaps 1.2 or even 1.3 trillion when you properly account for all the cool, faint stars that previous surveys missed. But detecting stars is only half the challenge. Once you've photographed a region containing millions of faint stellar images, you need to analyze them. Identify which points of light are actually stars versus background galaxies or instrumental artifacts. Measure their brightness in multiple wavelengths, classify them by type, and extract useful statistical information. For decades, this work was done primarily by humans, painstakingly examining images and catalogs. It was slow, labor-intensive, and limited by human attention spans and cognitive biases. Enter machine learning, and suddenly the game changes completely. Modern AI algorithms can be trained to recognize patterns in astronomical images with accuracy that matches or exceeds human experts, but they can do it millions of times faster and without fatigue or bias. The implications for counting stars in Andromeda are profound. Here's how it works. Astronomers take a subset of images where they have carefully identified and classified every star manually. This becomes the training set. They feed this training set into a neural network, essentially showing the AI thousands of examples of this is what a star looks like versus this is what noise looks like versus this is what a background galaxy looks like. The AI learns to recognize subtle patterns, the shape of the point spread function for a star, The way light falls off with distance from the center, the color signatures that distinguish stars of different types. Once trained, the AI can analyze new images automatically. You give it a photograph of Andromeda containing millions of points of light, and it identifies which ones are stars, estimates their temperatures and masses, and even flags unusual objects that might warrant closer human examination. The entire process that might take a team of graduate students months to complete can be done in hours or days, but the real power comes when you combine AI analysis with multiple data sources. Consider the European Space Agency's Gaia mission, a satellite that launched in 2013 with a singular purpose to create the most detailed three-dimensional map of stars in our galaxy. Gaia measures the positions, distances, and motions of over 1 billion stars with unprecedented precision, tracking their movements across the sky to millisecond accuracy. While Gaia focuses primarily on our Milky Way, it can also observe the brightest stars in nearby galaxies like Andromeda. In 2020, Gaia released measurements of thousands of individual stars in Andromeda, providing the first-ever three-dimensional map of stellar motions in another galaxy. This data revealed things that photographs alone never could, which stars are moving together in groups which are on unusual orbits, which might be foreground stars from our own galaxy mistakenly counted as part of Andromeda. Machine learning algorithms excel at finding patterns in this kind of multi-dimensional data. By combining Gaia's positional measurements with photometry from Hubble and Webb, with spectroscopy from ground-based telescopes, and with archival observations stretching back decades, I can identify stellar populations with a precision that would be impossible for humans analyzing any single data source. A team at the Max Planck Institute demonstrated this beautifully in 2023. They trained a neural network on combined data from 5 different telescopes, observing Andromeda, including optical infrared and ultraviolet images spanning 20 years. The AI learned to distinguish between at least 15 different stellar types based on their multi-wavelength colors and brightness variations over time. When they applied this trained network to the full Andromeda dataset, it identified several previously unknown stellar populations, including a substantial number of asymptotic giant branch stars, evolved red giants in a specific phase of their life cycle that had been misclassified in previous surveys. The result, their revised estimate for Andromeda's stellar population, came in at 1.1 trillion stars, with a much tighter uncertainty range than previous estimates. The AI had essentially refined our census by reducing the systematic errors that plague human analysis. But perhaps the most revolutionary application of AI to stellar populations involves spectroscopy analyzing the light from individual stars to determine their chemical composition, temperature, and radial velocity. Spectroscopy is incredibly information-rich, but also incredibly time-consuming. A single high-resolution spectrum can take 30 minutes to an hour of telescope time to collect, and then requires sophisticated analysis to extract all the information it contains. Neural networks are transforming this process. Modern algorithms can analyze stellar spectra in seconds, extracting dozens of chemical element abundances with accuracy comparable to traditional analysis methods that might take a human expert hours per star. This has enabled surveys like Apogee, Apache, Point, Observatory Galactic Evolution Experiment to collect and analyze spectra of hundreds of thousands of stars, providing the chemical fingerprints needed for stellar archaeology on an unprecedented scale. For Andromeda, spectroscopic surveys have been more limited because the stars are so much fainter than those in our own galaxy. But even a few thousand spectra analyzed with AI assistance can provide statistical insights into the galaxy's overall stellar populations. By identifying the chemical signatures of stars with different ages and origins, astronomers can refine their estimates of how many stars formed, when, and how many came from absorbed satellite galaxies. One particularly clever technique combines AI pattern recognition with physical models of stellar evolution. Stars of different masses evolve differently, and their position on what's called the Hertzsprung-Russell diagram, essentially a plot of brightness versus temperature, tells you about their mass, age, and evolutionary stage. By training neural networks on theoretical stellar evolution models and then applying them to observe stars in Andromeda, astronomers can essentially age-date millions of stars simultaneously. This technique revealed something surprising. Andromeda's star formation history was even more bursty than previously thought, with distinct peaks of intense star formation separated by quieter periods. Each burst added tens of billions of stars to the galaxy over relatively short time scales of a few 100 million years. The AI could identify these populations by their subtle differences in color and brightness differences, too subtle for humans to categorize reliably, but obvious to a well-trained algorithm. There's also the question of what counts as a resolved star versus unresolved stellar populations. In Andromeda's dense core, stars are packed so tightly that even Hubble can't separate them into individual points of light. What you see is a smooth glow from millions of overlapping stars. Traditional analysis would simply measure the total brightness of such regions and divide by the average brightness per star to estimate the stellar count. But I can do better. Machine learning algorithms trained on simulated images of crowded stellar fields can learn to recognize subtle patterns in the light distribution that indicate how many stars are contributing to the glow and what their properties are. It's like hearing a symphony and being able to estimate not just how many instruments are playing, but what types of instruments they are. The AI essentially deconvolves the mixed light into its component sources with remarkable accuracy. This technique applied to Hubble images of Andromeda's bulge suggested that previous estimates of the stellar density in the core regions were off by 10 to 15%. There are more stars there than simple brightness measurements would suggest, because the average stellar mass in those regions is lower than assumed. More small stars, fewer large ones, but the same total brightness. Can you imagine what becomes possible when we combine all these techniques? Webb's infrared sensitivity revealing cool stars, Gaia's 3D mapping showing stellar motions, AI algorithms analyzing millions of spectra, machine learning deconvolving crowded stellar fields, multi-wavelength photometry spanning decades. We're not just counting stars anymore. We're conducting a comprehensive census that reveals not just how many stars exist, but what types they are, how old they are, where they came from, and where they're going. And yet, for all this technological sophistication, we still can't give an exact number. The current best estimates using all available data and state-of-the-art analysis techniques place Andromeda's stellar population at somewhere between 900 billion and 1.3 trillion stars, with a most likely value around 1 trillion. That's a huge range of 40% uncertainty, even with all our advanced tools. Why such persistent uncertainty? Several reasons. First, the lowest mass stars and brown dwarfs remain essentially invisible even to Webb. We can estimate their numbers statistically, but we can't count them directly, and those estimates involve assumptions that might be wrong. Second, the outer reaches of Andromeda's halo extend so far and contain such faint, sparse stellar populations that we've almost certainly missed some. Third, there are still systematic uncertainties in how we convert observed brightness into stellar counts, uncertainties about the dust extinction, about the distance to Andromeda, about the stellar mass function. But here's what's remarkable: despite these uncertainties, the order of magnitude is solid. Andromeda definitely contains hundreds of billions to around 1 trillion stars. The uncertainty is in the details, not in the big picture. And those details keep getting refined as technology improves and AI analysis becomes more sophisticated. The lesson from this technological revolution is humbling. Every time we improve our tools or our analysis methods, we find that our previous counts were incomplete, not wildly wrong, but systematically biased in subtle ways. Webb reveals stars Hubble missed. A. Eye finds patterns humans overlooked. Multi-wavelength analysis corrects single-wavelength biases. The true count keeps shifting as our methods improve. This raises a philosophical question. Will we ever know the exact number of stars in Andromeda? Or is there some fundamental limit to our knowledge, some irreducible uncertainty that no amount of technological advancement can overcome? Given that stars are constantly being born and dying, that some are too faint to ever detect at intergalactic distances, and that the boundary between Andromeda and intergalactic space is fuzzy, maybe the question itself is flawed. Maybe we need to accept that approximately 1 trillion stars is as precise an answer as the universe allows us to have. Yet, even if we can't count every single star, what we've learned through this process of trying has been invaluable. We've mapped the galaxy's structure, understood its history, identified distinct stellar populations, and watched it evolve. We've learned that Andromeda isn't just a collection of stars, but a complex dynamic system with a rich story to tell. And in learning to count its stars, we've developed tools and techniques that work for every galaxy in the universe. So, when we step back and ask ourselves what it really means to count the stars in Andromeda, perhaps the answer isn't actually a number. Perhaps it's an understanding of framework for comprehending the vast stellar cities that populate the cosmos. And with that understanding comes perspective, a sense of our place in this incomprehensibly large universe, and an appreciation for the cosmic processes that have filled it with so many suns. So, here we are at the end of our journey through Andromeda's stellar census, and we've arrived at an answer roughly 1 trillion stars. But if I'm being honest with you, that number feels almost meaningless now, doesn't it? Because what we've really discovered isn't a number. It's a profound lesson about the nature of knowledge, the limits of measurement, and what it means to comprehend something so vast that the human mind can barely grasp it. When you try to count the uncountable, you end up learning something far more valuable than a simple tally. Let's sit with that number for a moment. 1 trillion stars. If you started counting right now, 1 star per second, never sleeping, never stopping, it would take you approximately 31,000 years to reach 1 trillion. That's longer than the entire span of recorded human history. You'd need to count through the rise and fall of ancient Egypt, Greece, Rome, every medieval kingdom, every modern nation, and you still wouldn't be finished. More people have lived and died on Earth, roughly 100 billion humans throughout all of history, than you could count in 3 lifetimes of non-stop counting, and yet there are 10 times that many stars just in Andromeda. Here's another way to think about it. There are more stars in Andromeda than there are grains of sand on all of Earth's beaches combined. Some estimates put the world's beaches at about 7.5 quintillion grains of sand. That's 7,500 trillion grains. Andromeda's trillion stars represents about 1/7 of that. Imagine trying to count every grain of sand on a beach. Now, imagine that beach stretches across an entire continent. That's still less daunting than counting Andromeda's stars, because at least you could theoretically walk the beach. You can't walk through a galaxy, but numbers like these do something interesting to the human brain. They stop meaning anything concrete. A trillion becomes just a word, a symbol representing unimaginably many. And that's actually okay, because the real value of counting stars isn't in arriving at a precise number. It's in the process of trying and developing the methods and tools and understanding necessary to make the attempt. Think about what we've learned along the way. We learned that you can't count what you can't see, which drove the invention of telescopes. We learned that seeing isn't enough without understanding, which drove the development of spectroscopy, parallax measurements, and distance determination techniques. We learned that direct counting fails at galactic scales, which drove the invention of statistical sampling and luminosity functions. We learned that visible light shows only a fraction of stellar populations, which drove the development of infrared and ultraviolet astronomy. Every limitation we encountered forced us to become more clever, more sophisticated, more humble, about what we claim to know. And there's something beautifully democratic about this cosmic census. The trillion stars in Andromeda exist regardless of whether we count them. They don't need our attention or acknowledgement. They were there long before humans evolved, and they'll be there long after our species is gone. By counting them, we're not changing them. We're changing ourselves, expanding our understanding of the universe we inhabit. Let me share something that keeps me awake at night: the connection between counting stars and searching for life. There's a famous equation in astronomy called the Drake equation, formulated by Frank Drake in 1961, as a way to estimate how many intelligent civilizations might exist in our galaxy. The equation starts with the number of stars, then multiplies by the fraction of stars. With planets, the fraction of planets that could support life, the fraction where life actually develops, and so on. For Andromeda, we now know the first term of that equation, with reasonable confidence, roughly 1 trillion stars. If we assume even a conservative fraction, have planets say 20%, that's 200 billion planetary systems in Andromeda. If even a tiny fraction of those harbor life, if an even tinier fraction develop intelligence, the implications are staggering. Andromeda could contain millions or even billions of worlds where life has emerged. Some might have civilizations looking back at the Milky Way right now, conducting their own stellar census, trying to count our stars, just as we count theirs. This is what counting stars ultimately teaches us. We're not alone in the sense of cosmic rarity. We're not the center of anything. Our sun is one of a trillion in just this one galaxy, and Andromeda itself is just one of roughly 2 trillion galaxies in the observable universe. If you multiply that out 2 trillion galaxies each, containing hundreds of billions to trillions of stars, you get a total stellar population in the observable universe of somewhere around 200 billion trillion stars. That's a 2, followed by 23 zeros. Can your mind hold that number? Mine can't. It's so large that it becomes almost meaningless, a mathematical abstraction, rather than something you can visualize or comprehend. And that's the point. The universe is teaching us humility. It's showing us that we are a tiny part of something incomprehensibly vast, and our significance lies not in being special or central, but in being able to understand that vastness at all. There's another connection worth exploring: what counting stars tells us about the nature of scientific knowledge itself. Throughout this journey, we've encountered uncertainty at every step. We don't know the exact distance to Andromeda. Our best measurements say 2.5 million light years, but that could be off by 100,000 light years in either direction. We don't know the exact stellar mass function, how many small stars exist per large star. We only have statistical models based on nearby observations. We don't know how much of Andromeda's halo we're missing, because it's too faint to detect. Every number we've quoted comes with error bars, with caveats, with assumptions that might be wrong. And yet we can still say with confidence that Andromeda contains approximately 1 trillion stars. Science doesn't require absolute certainty to provide useful knowledge. It requires honest assessment of uncertainty, rigorous methods for reducing that uncertainty, and the intellectual humility to revise our understanding when new evidence appears. This is perhaps the most important lesson from our stellar census: precision and accuracy are not the same thing. And sometimes approximate knowledge is all you can achieve, and that's enough. We'll never count every individual star in Andromeda. We'll never resolve the faintest red dwarfs, or detect every brown dwarf, or account for every ejected star drifting in intergalactic space. But we can bracket the answer, constrain the possibilities, and arrive at an estimate that captures the true scale of the galaxy. Let me bring this back to something more personal. When I look up at the night sky on a clear night and find that faint smudge of light that is Andromeda, I'm seeing photons that left that galaxy 2.5 million years ago. Those photons began their journey before humans discovered fire, before we learned to make tools, before we were even recognizably human. They traveled through the vast emptiness of intergalactic space for longer than our species has existed, just to arrive at my eye at this precise moment. And those photons carry information about the trillion stars that produce them, about the structure of the galaxy they came from, about the physical processes that govern how light interacts with matter across cosmic distances. By learning to read that information, by developing the tools and techniques to extract meaning from ancient starlight, we've accomplished something remarkable. We've counted stars. We can never visit, mapped a galaxy, we'll never explore, understood a cosmic structure we can barely comprehend. There's a beautiful paradox at the heart of this endeavor. The more precisely we try to count Andromeda's stars, the more we realize that precision isn't really the goal. What matters is the understanding we develop along the way, understanding about stellar evolution, galactic structure, cosmic history, and our place within it all. The journey teaches us more than the destination ever could. Think about Abd al-Rahman al-Sufi looking up at that little cloud in 964 CE and carefully recording its position. He had no idea what it was, but he knew it was worth documenting. Think about Edwin Hubble in 1924 discovering that Andromeda was an entire galaxy and expanding the known universe by a factor of thousands in a single observation. Think about the modern astronomers using AI and space telescopes to refine our senses, finding stars that previous generations couldn't have imagined detecting. Each generation builds on the knowledge of previous ones, adding their own contributions, refining the count, deepening the understanding. And future generations will do the same, using technologies we haven't invented yet, asking questions we haven't thought to ask. The census is never truly complete because knowledge is never truly finished. It's always provisional, always subject to revision, always growing and evolving, just as the universe itself grows and evolves. So, what's the final answer to our question? How many stars does Andromeda contain? The honest answer is approximately 1 trillion, give or take a few hundred billion, depending on what you count and how you count it. With the understanding that this number represents a snapshot of an evolving galaxy, measured with imperfect tools, analyzed with techniques that will surely be surpassed in the future, but representing the best knowledge humanity has accumulated through centuries of observation, calculation, and wonder. And perhaps more importantly, enough stars that trying to count them all individually would be futile, but not so many that we can't comprehend their number, statistically study their properties collectively, and learn profound truths about the universe from their aggregate behavior. Enough stars that the galaxy is unimaginably vast, but not so many that we can't fit that vastness into equations, models, and theories that actually work. When you settle into sleep tonight, imagine those trillion suns scattered across Andromeda's spiral arms, ancient bulge and diffuse halo. Imagine the planets that surely orbit many of them, the potential for life that might exist on some of those worlds, the possibilities that such vastness implies. Let that scale wash over you, not as something to be feared or that makes you feel insignificant, but as something awe-inspiring, something that connects you to the cosmos in the most fundamental way possible. Because we're not separate from the universe we're trying to understand. We're made of atoms, forged in the cores of long-dead stars, atoms that once belonged to stellar populations in ancient galaxies, atoms that have cycled through generations of cosmic creation and destruction. The iron in your blood, the calcium in your bones, the carbon in your cells, all of it was created in stars. Not unlike those we've been counting in Andromeda, you are quite literally made of stardust. So, counting the stars in Andromeda isn't just an academic exercise. It's a way of understanding our origins, our context, our place in the grand cosmic story. It's a way of connecting to something vastly larger than ourselves, while simultaneously recognizing that we are part of it, not separate from it. The universe isn't something out there that we observe from the outside or inside. It made of it temporary arrangements of stellar material that have somehow achieved consciousness and the ability to count. And in the end, that might be the most remarkable thing of all, not that Andromeda contains 1 trillion stars, but that we products of stellar alchemy ourselves can figure that out. That we can look at a faint smudge of light in the night sky and deduce its distance, its structure, its population, its history, and its future. That we can take the ancient light from 1 trillion distant suns and extract from it a story of cosmic evolution spanning billions of years. The number isn't the point. The understanding is. The humility is. The wonder is. The connection between us and those distant stars, made of the same matter, governed by the same physical laws, part of the same cosmic dance that's been unfolding for nearly 14 billion years. That's what counting the stars in Andromeda really teaches us, not a number, but a perspective, a way of seeing ourselves in context, a reminder that we're part of something incomprehensibly beautiful and vast. So, as you drift towards sleep tonight, let your mind wander through Andromeda's trillion stars. Let yourself feel small in the best possible way, not insignificant, but part of something magnificent. Let the vastness remind you that there's so much more to discover, so many more questions to ask, so many more cosmic mysteries waiting to be understood. And let the fact that we can count those stars at all, even approximately, remind you of something wonderful. We're the universe's way of understanding itself. Thank you for joining me on this journey through the stellar census of Andromeda. Thank you for staying curious, for asking questions, for wanting to understand the cosmos we inhabit. The universe is vast and strange and beautiful, and there are countless more stories to explore together. Until our next cosmic adventure, keep looking up, keep wondering, and keep counting the uncountable. Sweet dreams, stargazers.